Good afternoon. This is lecture 2 of the FIR filters series. Now, last lecture we discussed what an FIR filter is. An FIR filter is a type of digital filter implemented on a computer. Remember that it has these steps. Step 1, choose parameters for the filter. Step 2, choose impulse response of the filter. Step 3, choose window function. Step 4, multiply window function with impulse response. Let me just do that again. Impulse response, and then step 5, convolve the results of step 4 with input to signal. Now today we're going to be looking at step 1, choosing parameters for your filter. Let's do that. Okay, there are a large number of parameters you can choose for an FIR filter. There are an endless list of them. Some are very advanced ones to look at, some are a bit more basic. We'll stick with the basic ones, so parameters. So the ones we will look at today are the filter function, cutoff frequency, and then finally the filter order. These three are the most fundamental filter parameters, the most basic ones, easiest to understand, so we'll look at them now. Now, the more advanced parameters we will be looking at later in the course, but ideally I don't want to overcomplicate things, so let's look at the basics. Let's start with filter function. Filter function. Now, if you are familiar with filters, you're probably aware of low pass filter, high pass filter, band pass, and then stop, band stop. Your main types of filters. Low pass filter, let the low frequencies pass through, the high frequencies are attenuated. High pass is the opposite, let the high frequencies pass, let the low frequencies are attenuated. Band pass means you allow a range of frequencies to pass through. And then finally, band stop means you attenuate a range of frequencies. Let's look at that. Okay. Low pass filter. We'll look at low pass filter for now. Low pass. So it has a frequency response like this. So that's frequency now. Goes like that. So here we have high frequencies. Amplitude is basically 0. Then we have over here the low frequencies. Then at this point here, before you roll down here, you have your cutoff, which we'll look at later. Cut off frequency. That's it, simple. Now the high pass filter. High pass is the exact opposite. So see amplitude. The low frequencies cannot pass through, but the high frequencies can pass through. So your high frequencies, your low frequencies, and finally your cutoff here. Simple. Now, band pass. Band. Again, we remember we allow a range of frequencies. So that's the high cutoff. So this is the high attenuated and the low attenuated ones. And here's a range of frequencies you let through. You can call that cutoff 1, cutoff frequency 2. And then finally the band stop filter. Band stop filter is the exact opposite. Frequency amplitude. We allow the lowest lower frequencies to pass through up till a point. Could call that cutoff 1. And then up till another point, cutoff 2. And anything in between here, they are attenuated. All the other frequencies are let through. Now some applications. A low pass filter, you may want to remove say 50 hertz noise or anything under your frequency, maybe low frequency noise too. High pass filter, if you have a lot of high frequency noise, which is a very common one with amplifiers, high frequency noise can be removed with a high pass filter. Band pass filter allows you to narrow it down to the frequencies you want exactly. So that removes the most noise. You can remove any low frequency, unnecessary noises. You can remove any unwanted signals at the top. And then band stop is quite an interesting one because you can make it very selective to the point that it only removes very few frequencies. So electrical noise, like from the 50 hertz line, or in America 60 hertz line, electrical lines, they release 50 hertz noise, 60 hertz noise, and a band stop filter can be used to eliminate any 50 hertz noise you have in your electrical system. So yeah, basic applications. The applications go on forever, of course. Okay, next look at the cutoff frequency. You probably already know cutoff by now, but let's look at it again. So when you have a filter, so this is a low pass filter, as an example, you have this point cutoff. But what exactly is a cutoff frequency? Well, the cutoff frequency is 0.707 off the max amplitude. So if you have a sine wave and that is 1 volt, well, the cutoff frequency will be for any frequencies at 0.707 volts, and that's regarded as attenuated. Now, of course, if you're at 0.707 volts, you'll probably still see that in your main signal. So how good of a cutoff that is, well, that depends on your specifications, of course. And there are some more important things to look at with this. Well, there are actually 3 parts of this low pass filter. There's a pass band, your pass band, and these are the frequencies that are allowed through. Frequencies allowed through. Then you have your stop band over here. Stop band, which are frequencies that are blocked. And then finally, you have some part in the middle here. And this part is called a transition band. And these are the frequencies after the cutoff. So the transition band starts at the cutoff frequency, and then all the frequencies that are rolling down here until the stop band, that is the transition band. Now that comes to our next parameter, which is filter order. Now filter order, if you can just read this. Filter order. Now the higher your filter order, the smaller your transition band. A higher specification filter will have this region here smaller. So a better filter would probably look like this. So cut off there, and you can see it has a very, very small transition band. And this transition band is a lot better than that. Sometimes this red transition band is unacceptable because this frequency here may still be fully present in your signal even though it's after the cutoff. So you want a higher filter order because it allows a smaller transition band. It allows a steeper frequency response, which is good. Now let's look at the ideal. An ideal filter looks like this. You see, it is a rectangle. It has no transition band, and it's ideal. It doesn't exist, of course, but that is ideal, and that's what the most wanted filter would be, of course. We know that we want a higher filter order because it's higher performance. Remember, smaller transition band is a higher performance, more selective filter. But what's the problem with that? Well, a higher filter order also means higher computational power. And sometimes your computer cannot compute a very high filter order. High filter orders, of course. That means that you have to make a sacrifice between your filter order and the computation power and the performance of your filter. You don't want too much computation power or your computer cannot survive. And you don't want too little performance, otherwise your filter is practically useless. So you must find a happy middle between performance and computation power. I think I should stress that point more. Always want good performance, but you don't want to be using too much computation power. So sacrifice computation power and filter performance. As long as you can find a good middle between these two, you have a good filter. Now, more often than not, you can see. So, next lecture, we will look at choosing impulse responses. Choosing impulse responses. Well, today, hopefully, you've learned about parameters, choosing parameters, and the different types of basic parameters. Well, that will be carried on to next lecture, where we will look at impulse responses. Thank you. Please like and subscribe. See you next time.